Thank you. Thank you. It's great to be here, and I really appreciate all the viewers. Thank you guys for tuning in. I'm going to talk about something that I think a lot of people don't really understand about how science works. So now arguments over any scientific topic, whether it's climate change or vaccines or you name it, they revolve around competing scientific claims. For climate change, is the earth warming? Are humans to blame? What are the impacts going to be? And over the last 150 years, the scientific community has developed this really remarkably robust method to determine which claims are true and which are not. And this is what I'm going to talk about. So anyway, how does science generate knowledge? So if you ask a high school student, how does science work? They'll give you the high school definition, which they learned in ninth grade science, which is you have an individual scientist makes a hypothesis, conducts an experiment, and draws a conclusion. And this is more or less what actually happens at the individual level, although it's a bit more iterative than that, where experiment, hypothesis, design are kind of happening at the same time. And you come up with an idea and you kind of do some analysis, and it wasn't quite right. So you come up with a slightly different idea. But nevertheless, at the end, you've reached some conclusion about whatever hypothesis you've ended up with. Now, this is not science, though. This is step one of science. And the reason is any individual scientist can make mistakes. Scientists are human. They make errors. And maybe there's a bug in their code. Maybe they made a mistake in their experiment. And so just because someone's done an experiment, reached a conclusion, doesn't mean it's right. And so scientists don't take the results of an individual experiment as being like, okay, this is now correct. So what's step two? Well, step two is the scientist writes up their report, what they did in an article, and then they submit it to a journal, and it goes through peer review. And this is the first layer of quality control in the scientific world. And during this process, they send the report to other experts in the field, and the other experts in the field judge whether the methods are sound, if it appropriately references previous work, if the conclusions logically stem from the data. And if you ask any scientist, they will tell you peer review is miserable because you get brutal comments back. I mean, I cannot tell you how brutal it is. And you have to go through this cycle of, you get comments back from the reviewers, and oftentimes they can be mean, and they can, it's very tough, and they're criticizing your work. You spent a year on this, and so you have to revise it, and it goes back to the editor, and the editor will sometimes send it back to the reviewers. And so you really have to respond well to those comments. And so in order to get it published, it has to go through this process. And eventually, if you write a paper, it goes out for review, it comes back, you fix it, maybe it does it a couple of times, the editor will eventually accept the paper. Now, peer review is really good, and it catches an immense amount of bad science, but it can't catch all bad science. Some reviewers are sloppy, some reviewers are overworked. Sometimes they just miss, they're humans, they miss obvious mistakes, and they can't catch hidden errors. Like there's a bug in the code, so it wasn't doing exactly what you described it was doing, or maybe you misread a lab scale. And so peer review is the first step of quality control, but it's not the last. Just because a peer-reviewed paper makes it into the journal doesn't mean the paper's right. And nobody thinks a single peer-reviewed paper is right. So then what happens is important results are retested by the scientific community. I like to call this the crucible of science. So if you write a paper that's really interesting and you release it, it will get dissected by the community at that point. And in some cases, people will try to reproduce what you did. That actually doesn't happen that often, maybe more in lab experiments than in computer experiments. But more likely what they do is they test the implications of it. If you say X is true, you might say, well, if X is true, then I can look at Y, because Y will also be true. So you can you can test the implications of it. And if something survives long enough, then the claim is accepted. So this is how we generate knowledge. So let me give you an example. All right, let's go back to the ozone hole. So 1985, I'm sure very few of the people watching were around in 85. I remember 85 well. 1985, the ozone hole was discovered. And Joe Farman and his colleagues published the observations taken from Antarctica showing that every year the ozone, a big chunk of ozone over Antarctica was disappearing. And this was shocking because up until the discovery, most atmospheric chemists thought that most of the ozone that was going to be lost would be lost at mid-latitudes and high altitudes. So this loss was happening completely in a place where nobody thought loss would be occurring. So immediately, when you see something you don't understand, scientists started trying to fill the void. And so a bunch of theories emerged, which were all published in the peer-reviewed literature, by the way, that argued about different possible causes. So the first one was chlorine chemistry. So here's a paper by Susan Solomon and a bunch of other big names in the field arguing there was chlorine that came from fluorocarbons. Another argument is that it was nitrogen chemistry, not chlorine chemistry. And the nitrogen could have come from solar proton events. In other words, it was the sun that was doing it. And the third claims that it wasn't chemistry at all, but it was dynamics. If there's very low ozone air in the upper troposphere, and so if you have rising motion, then you'll bring that low ozone air up into the lower stratosphere. And so that's a different way of getting very low ozone air in the lower stratosphere. And so we had these three theories, all published in peer-reviewed literature. And so then the scientific community went to work on testing which of these stood the test of time, which of them could survive in the crucible of science. And so pretty quickly what happened is they flew into the ozone hole and they measured nitrogen and they saw there was no nitrogen there. So it couldn't be nitrogen that was destroying the ozone. So they were able to rule out reactive nitrogen as the cause of the ozone depletion. And then people were doing various calculations and measurements. They realized that the air in the polar vortex was descending. That would bring high ozone air down. It was not rising. So you could eliminate the dynamic theory. And then there was the chemistry. Well, they were, again, the same planes that were measuring oxides of nitrogen in the polar vortex were also measuring chlorine, and they saw there was a ton of chlorine there. And they saw that the chlorine very strongly correlated with the regions where the ozone was depleted. And so people refer to that as the smoking gun paper, really established that it was chlorine chemistry that was destroying the ozone. And so what basically happened through this process is a consensus emerged as to what was going on. Now, it's important to understand, you often hear people talk about scientific consensus. Let me make the point, consensus is organic. There's no vote, there's no poll, there's no meeting to decide what it is. What it means is that people go to meetings, I talk to other people, and pretty soon, everyone kind of independently decides this is the right answer. It's the ultimate free market of ideas. And if you read any peer-reviewed paper after the late 1980s, they don't even talk about these other theories. They just take it as given that chlorine chemistry is responsible. And so this is what we mean when we say a consensus has emerged. It doesn't mean every single individual scientist agrees with that, but it does mean that there really is no legitimate debate about the issue. All right, so this then brings us to the question of where can you see, or anybody else, what scientists think? Well, it's in the peer-reviewed literature. If you read the peer-reviewed literature, you see the entire historical record of the argument. You see the ozone hole being discovered. You see the theories emerging about what it could be. You see the debate about those theories happening. You see testing of rival hypotheses. And then you see the community coalescing around one of them. That's consensus. And so, just read the peer-reviewed literature. Now, I will point out that there's a lot of opportunity for people to misrepresent the literature, because you can go into the literature, and if you go back, you can find papers that say the ozone hole is caused by dynamics. And somebody says it's fluorocarbons and chlorine. You can say, oh, but I have this paper from these famous scientists that say it's dynamics. And what they don't tell you is like, well, that idea was disproven and nobody believes that's correct anymore. Even by the authors who wrote those papers, they just don't talk about it. So the peer-reviewed literature is there, but what's the problem with this? So the problem is that the peer-reviewed literature is written in a language I call nerd. So this is something I just cut out of a paper, and it's extremely hard to understand. So don't even try to read this. It's even hard for me to understand, and I wrote it. So, reading the peer-reviewed literature is incredibly hard. And, it takes graduate students years to read all the literature in a field. And so you can't really expect policymakers or individuals to read the literature. And so this is where scientific assessments come in. So what is a scientific assessment? Well, the one you've probably heard of most is the IPCC reports, Intergovernmental Panel on Climate Change. And the fundamental role of an assessment is to read and summarize the peer-reviewed literature, doing exactly sort of what I described is the argument. So they summarize what's in the literature. They synthesize what's settled, what's disproven, what remains actively debated. And importantly, it's authored by large teams of scientists. And that's important because large teams are less likely to be biased than small teams. It also means that the impact of any individual biased scientist is minimized. The teams are assembled to avoid bias. Like they don't let one single person who might have an axe to grind pick members of the committee, because he could stack it with people who all believe one theory. And so they don't do that. And in addition, the report undergoes several rounds of peer review itself. So the scientists write it. It goes out to other scientists. They write comments. It goes back to the authors. They edit it. It goes back out to the peer reviewers. It comes back. It goes through many rounds of peer review. And the credibility of these reports comes from this rigorous process. That really is why you can believe them. It's the gold standard. And if you see an assessment that's written from a different process, it very likely might not be credible. You can actually see, if you look at them, you can see the evolution of consensus. So I'll just give you one example about attribution of warming. So in the 1990 IPCC report, it said the size of the observed warming is broadly consistent with predictions of climate models, but is also the same magnitude of natural climate variability. Thus, the observed increase could largely be due to this natural variability. So the 1990 IPCC report said, we don't know why it's warming. Maybe it's humans, maybe it's not. We just don't know. 1995, the second IPCC report said the balance of evidence suggests a discernible human influence on global climate. That, by the way, is the definition of a sentence that could only be written by a committee. Basically, it doesn't say much. It says, humans are having some influence. We don't know how big it is, and maybe it's not having any influence. In 2001, the evidence was getting stronger. The consensus was emerging. Most of the observed warming in the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. 2007, most of the observed increase in global average temperature since the mid-20th century is very likely due to the observed increase in greenhouse gas concentrations. So we went from likely in 2001 to very likely in 2007. And then in 2013, it's extremely likely. So you can see the consensus emerging over time in these things. The 2023 report basically says the same thing as 2013. It can't get a lot stronger than that. And so you can see this occurring in the assessment reports. So I'll just wrap up here. How does science work? Well, let me start by saying science is our ultimate tool for deciphering the universe. It's what we've developed is the most successful way to determine what is true and what is not true. And the understanding of science is written into the peer-reviewed literature. So if you want to know what scientists think about something, read the literature. Now, it's hard to do for people that don't speak nerd. And so in those cases, rely on scientific assessments. They are what I call the Rosetta Stone. They translate nerd to English. Anyway, hopefully there's some interesting questions. I love talking about this, so I will open the floor. Thank you.